Hey kids, Mr. Murray here again, just trying another one of these videos. It's either this or I show up outside your house and bring an easel and try to do this through your front window. So let's give this a try, shall we? Hope everybody's doing well this first week of remote learning. But we're going to take a look at a different way to describe the graph of a parabola. Here we have on Desmos y equals x squared, basic parabola opening upwards with its vertex at 0, 0. And we've been looking a lot at the equation of a parabola in standard form, which is y equals ax squared plus bx plus c. And getting the vertex is negative b over 2a, well, the x-coordinate of the vertex, that is. So we've looked at these two examples over here, y equals x squared plus 2. When I throw plus 2 on the end of that, what's going to happen to that? I pause for dramatic effect there, but it's going to go up 2. It shifts up 2 units, or what we call a translation of 2 units upwards. This y equals x squared minus 3, it's going to shift 3 units down, and there's its vertex at 0, negative 3. And we talked about these really on the first day, that whenever b is 0, of course that's going to make negative b over 2a. That's going to be 0 over 2a. You're going to get the x-coordinate at 0. It's just going to shift up and down, or as we call it, a translation, up and down. But what about these? These last two examples aren't really in standard form at all, because they have the plus 2 on the inside of parentheses with the squared on the outside. So just think about this. It's not standard form. It's got its own rules here. When I plug in 0 into the original y equals x squared function, I get out 0 for y. But when I put plus 2 on the inside, whatever x value you plug in is going to get 2 added to it before you square it by order of operations. So just think about it this way. What x value would you need to plug in order to get 0 out for y? And that might help you see where this is going to go, because a lot of people, when you see plus 2 add to the x, they think of moving 2 units to the right. They think of positive 2, but really, as you can see, it moves 2 units to the left. Its vertex is at negative 2, 0. And that's because what I just said, if you were to plug negative 2 in for x, negative 2 plus 2 gives you 0, and now you'll get that same value of 0 out that you used to get out on the original at 0, 0. So y equals the quantity x minus 3 squared. Guess where the vertex is going to be? That's right, it's going to be at positive 3, because that's the x value that makes the inside 0. So a lot of times people will just sort of get the hang of this and say, hey, if I see minus 3 on the inside, that's going to move to positive 3. It's got that opposite effect. Plus 2 on the inside moves 2 units to the left. But it can be a tricky thing. So let's just take a look at these examples. And you see each of these has a couple things going on. This first example, we've put minus 4 on the inside of the parentheses before we're squaring it, and then plus 1 on the end. So this is really going to do both of our translation rules at the same time. Minus 4 on the inside is going to make it move to positive 4 to the right. And adding plus 1 on the end of a function does the same thing it always did. It moves it up 1 unit. So this vertex is going to be at 4, 1. 4 to the right, up 1. Now this set of parentheses, I put plus 1 on the inside. So what x value is going to make that 0? Negative 1. Then I put plus 2 on the end. So its vertex is going to be at negative 1, 2. But I've also thrown a negative out in front. So this shouldn't be surprising. We know when we throw a negative out in front, that is going to make the graph do this, open downward. So we have shifted it 1 unit to the left and 2 units up. That's a translation of 1 unit to the left, 2 units up, and I threw a negative out in front, which reflects it over the x-axis. That's what a negative always does. This one right here, +3 on the inside, -1 on the outside, no negative. That's going to be a vertex of -3, -1. The opposite of what you see in here, and just whatever you see there. -3, -1, and you can see its vertex is right there. Get a little congested there. And this right here, -2 on the inside. It's going to go 2 units to the right, and then -3 down, and that negative is going to make it open downward, a flipped upside down parabola, basically. All right, 2, -3. Again, make that connection. If you see -2 on the inside, it's gone to +2 on the x-axis. -3 on the end, it goes down 3, like it always did. And you put minus out in front, it flips it upside down. This is what we call vertex form of a parabola, because I don't really need to do any special formulas to find the vertex. I can see it right in the equation if you know the trick for looking for it. So this form with the parentheses squared, the quantity squared, they call this vertex form. And just looking at these last examples, there's one more little transformation, as they're called. All these things, reflections, translations, and what we're going to talk about now are called transformations of a graph. You know, things that affect the shape of the graph and where it's moved. Y equals x squared, yes, we know it's got this, its vertex is 0, 0. When I multiply it by 2, I haven't shifted it up or down, left or right at all. It's still going to be opening up. But watch what effect multiplying it by 2 has. And if you could probably think of it yourself, if you plug in 1 for x, now you're going to get 2 out for y. And so look at it. It's still a parabola with its vertex at 0, 0. But look what's happened. It's basically a skinnier version of what it used to be. And that should make sense, because if you think of what y equals x looks like, it's a line. And when you think about what y equals 2x looks like, it's a line, but with a greater slope. It's increasing faster. It's steeper, right? Well, it's really the same idea as on a parabola. There's a parabola, and it's got a nice rate of change here, this quadratic growth. But when you put a 2 out in front, it's like a parabola, but with a steeper slope. And so y equals 4x squared, you might imagine, is going to have an even steeper slope, or a greater rate of change. That is going to be an even skinnier version of the parabola. If I make that coefficient bigger, it gets even skinnier. And what we call this is not a skinny version of a parabola. They call this a vertical stretch, because if you can imagine, there's like some invisible hands on the top. It looks like somebody has taken this red parabola and kind of stretched it upward like a rubber band, with its vertex staying right at 0, 0. So picture pulling that up, and you get that kind of stretched vertically appearance, that skinnier looking parabola. They call that a vertical stretch. As you might imagine, this graph right here, 1/2 x squared, the coefficient of 1/2 now means it's got a slope, if you want to think of it that way, of 1/2. So you see what happens is the opposite. You get a wider looking parabola. 1/4, that's an even flatter slope, an even smaller rate of change. And so you get an even wider parabola. I make that even a smaller value. 1/8 is smaller than 1/4. It gets even wider. It can be in decimal form. It doesn't have to be a fraction. 0.01, that's a really, really wide parabola. Still with its vertex at 0, 0, just really wide. Okay, so look at this one function right here. This is kind of putting it all together, all the things we've talked about. I've got a -2/7 out in front. I've got a +5 on the inside of the squared quantity and a +1 on the end. So that is going to make its vertex be at negative 5, positive 1. So 5 to the left and 1 unit up. It's going to be opening downward because of that negative. And this 2/7, the fact that that is less than 1, if you focus on the absolute value of it, not the negative part, 2/7 is less than 1, that means it's going to be a wider parabola, or what we call a vertical compression. A wider one is a vertical compression. So check it out. Vertex at negative 5, positive 1, it opens down, and you can tell it's a wider version or a vertically compressed, the opposite of the stretch here. If that's a stretch, this is a compression, because it kind of looks like somebody has taken the original one and kind of squashed it vertically, and it's making it bow outward. Okay, well that's it for this Desmos exploration. Let's take a quick look at the worksheet examples, and then you're good to go with the homework for the night. Okay, so let's summarize from that Desmos demonstration and just hit up a few examples before you're off and running with the homework. Hopefully this straightens it out for you. This right at the top just summarizes here that this is what's called vertex form of a parabola when it's got this quantity squared, as opposed to standard form, which is the form we were working with. And standard form looks like that. Remember, that is standard form. So now you know two forms, and we're going to graph these in the next couple days. But when it comes to graphing, you always want to find that vertex first, so it matters which form you're in. This is great for finding the vertex because you can see it without doing any work. The vertex is always going to be at HK. Right? If you see minus h on the inside, that means it's going to actually move to positive h, whatever makes the inside 0. And then plus k, like always, moves it up or down depending on what that constant on the end is. The axis of symmetry, of course, would always be at x equals h. That goes right down the middle. And a, that coefficient controls two things: the direction of the opening, either up or down, or as we call that, a reflection over the x-axis. And if a is greater than 1, less than 1, it's a stretch if a is greater than 1, and it's a compression if a is less than 1. I guess I should say the absolute value, because you disregard whether it's positive or negative, just looking at that value and thinking about that slope. So here are some quick examples here. These are all in vertex form. This one right here, nothing has been added to the inside before it's being squared, so 0 squared is 0. So x-coordinate is at 0, but minus 6 on the end moves it down 6 units. So 0, negative 6. For the opening, stretch, and compression, you'd be looking at this coefficient. It's positive 1. So it's positive, so it'll be opening up, no reflection over the x-axis. And it's just 1, so we haven't changed the slope of this. It's that normal parabola shape, so neither a stretch nor a compression. This one right here, minus 6 on the inside. Now it's going to take positive 6 to make the inside be 0, or if you're in that habit of you see minus 6, that actually means it moves to positive 6 units to the right, and nothing added to the end or subtracted means we haven't moved up or down at all, so 6, 0. A negative out in front, and that's really a negative 1 coefficient right there. It's negative, so it opens down. It's a reflection over the x-axis, but it's still just a 1, so we haven't changed the stretch or compression of it. So it's still neither, only if it's something other than 1 or negative 1, like in this one you're going to see. So first, the vertex, we haven't added anything or subtracted anything to the inside before we square it, so there's no parentheses, so we haven't shifted it left or right at all. It's at 0, but straight up 4 units, so 0, positive 4. That coefficient out in front of 5, 6 is positive, so we would be opening up, no reflection over the x-axis. And 5, 6 is less than 1, so if you think of a slope of 1, 5, 6 would be slightly flatter, which would make a wider parabola, or as we call that, a vertical compression. It's been kind of squashed, making it look wider. Right here, part D, plus 4 on the inside means we're really going to go 4 units to the left because it takes negative 4 to make it 0. And on the end, nothing has been added or subtracted, so negative 4, 0. That's where our new vertex is. Leading coefficient is positive, so it opens up. And 3 is greater than 1, so if your slope is 1 normally, now it's 3. It's going to be increasing much quicker. That's going to appear as a vertical stretch. And last few examples right here. Once you get the hang of this, you can fly through these though. Plus 4 on the inside makes it move 4 units to the left. Plus 7 on the end makes it move 7 units up. Opposite of what you see, same as what you see for the y coordinate. Leading coefficient is negative, so that opens down. And it's 1/3, which would be a flatter slope, which is a vertical compression. Next one, very similar, minus 5 on the inside means it moves to positive 5 on the x-axis, plus 11 on the end, 11 units up. The leading coefficient is positive, so it still opens up, and 0.75 is less than 1, so again, it's going to appear vertically compressed. Plus 7 on the inside for part G moves it 7 units to the left. Minus 3 on the end moves it down 3. Opposite of what you see, same as what you see. Leading coefficient is 1, positive 1 that is, so it opens up, and no stretch or compression. We haven't changed that slope at all. And lastly, right here, minus 13 on the inside moves it 13 units to the right. Negative 5 on the end moves it 5 units down. Leading coefficient is negative, so that parabola is opening down, and 2 is a steeper slope than 1, so it's going to be vertically stretched. Okay, so now you can try your homework on the worksheets. If you need to use Desmos to check your answers, to see it, great. I encourage you to do so. The goal is by the end of it, you should be able to answer all those questions without looking at the graph, or really without doing any calculations, just by looking at the equation. All right, so let me know if you have any questions. Feel free to reach out and email. Good luck, guys.